The final topic we'll look at in Chapter 21 is trends in absolute entropies and sort of making sense of them and understanding what's happening on a microscopic level to lead to these trends. So in absolute entropy, at least in the notation that's used by your textbook, we write S bar naught, the bar here meaning this is a molar value, so we're thinking about what's the entropy of 1 mole of our substance, and this naught is to indicate that this is an absolute entropy. And so if we can find these for different substances. So in general, you can find exceptions to this, but in general, the absolute entropy of a solid will be less than the absolute entropy of a liquid, which will be less than the absolute entropy of a gas. All right, and this makes sense because in a solid, your material is more confined, and fewer energy levels are taken up, and so your value of W will be smaller. And so, or if you want to think about it in terms of disorder, right? A solid is much more ordered than a liquid, which is much more ordered than a gas. And we could probably even put two less than signs, right? A gas has much higher entropy than any condensed phase because of the much larger space it has to occupy, has many different energy levels it can access. So, and this makes sense, just thinking in terms of disorder, right? As solid, we have less disorder, and as we go to a gas, we get more disorder. So the entropy increases accordingly. Now, one other trend we can look at, let's look at something where everything's in the same phase. So we're going to look at some noble gases and what the entropy values are for those. So what's S bar naught? This is in units of joules per mole times Kelvin, since they're molar values. So helium has an absolute entropy of 126.2, neon 146.3, argon 154.8, krypton 164.1, and xenon 169.7. One nice thing here is that we're looking at just monotopic substances. They're all gases, so really what we're looking at here is the mass, right? The atomic mass and how that affects the entropy. And we can see a very clear trend here, right? As we go down the periodic table, as the mass increases, the entropy, absolute entropy increases. And that's generally true, that S increases with mass. Now, why is this? This has to do with the energy level spacings when we're thinking about these atoms moving around or gases moving around. The heavier something is, the energy levels are more closely spaced. So greater mass means closer energy levels. And the closer the energy levels are, the more the molecules can spread out in them. Right? So compare that versus this. Right, our molecules are able to spread out more here, whereas here they're sort of stuck in just a couple. And so accordingly, as we increase the mass, the entropy, I've exaggerated it here, but the entropy will increase as we increase the mass because those energy levels are spaced closer together. Now, one other trend we can look at as we move beyond just thinking about single atoms like a noble gas, we'll move over here, is thinking about the number of atoms in a molecule, for example. So if we look at some simple hydrocarbons, so starting from acetylene, C2H2, and we're going to compare everything in the gas phase here. The entropy here, so we're considering again S bar naught values, is less than the entropy of C2H4 gas is less than the entropy of C2H6 gas. Right, so as we add more atoms of a given type into a molecule, that leads to a larger entropy. And this is mostly due to the fact that we have an increase in the number of ways the molecule can vibrate. And that again gives the molecule more ways to spread out energy, which as we understand from the statistical interpretation of entropy, that increases W, which will increase the entropy for our substance. So the more atoms it has, the more vibrational modes it'll have, and it also increases the mass, which goes with the previous effect that we talked about as well. Now, if molecules have a similar weight, One other thing you can do to determine entropy is look at the rigidity of the molecule. So if you have, similar weight, but you compare how rigid it is. So for example, if you have something that is, say, a ring structure. So let's look at, this ring system here, this heterocycle. I don't even know what to call this one. But this restricts movement, and so the molecule can adopt fewer configurations. So this will have a smaller entropy than something like with the same number of atoms and the same, so an isomer, but arranged in completely different, right, where we have acetone here. These methyl groups are free to rotate. And that will increase the number of possible energy states, which will increase the entropy. So the entropy of our more restricted molecule will be smaller than the entropy of the more free to move molecule. And so that's another trend that we can see. And so you'll get some practice with this with some homework questions, but these are some general trends in terms of absolute entropy and thinking about what's happening on the molecular level to drive these changes in entropy.